Hello, looking to start chapter 4 here. One of my favorites, or actually my favorite, statistical concept here is covered in chapter 4. One I find the most interesting is percentiles and using data to compare, one individual to another or to a set of individuals. And so when we're looking, one thing you're probably familiar with is percentiles, especially with where you're at in your career, educational career. A lot of you are taking the ACT or even pre-ACT, and you might get or even the MCA, but you might get on your score back that you are in the such and such percentile. What does that mean? So the percentile is the percent of observations that are less than or equal to that observation. So in other words, less than or equal to you. So if you finish in the 80th percentile, that means you are better than 80%, or I should say better than or equal to 80% of the data in that population. So it's good to be in the 99th percentile if we're talking like test scores. It's not great to be in the 1 percentile for test scores, but that works both ways. There are definitely data sets that you don't want to be on the higher end of. Like BMI, I guess. If you're in a high percent of BMI, that means you're bigger and not as healthy. If you're in a lower percentage, then you're a little bit healthier. So it's not always that being in the 99th percentile is a good thing, but being in the 99th percentile just means that you are higher than or equal to 99% of the people in or of the data that was observed. It's just to note here that sometimes it's not less than or equal to, it is just below it. I would say less than or equal to is the general definition that pretty much everybody uses, but it is noted that sometimes they do use that to figure out the percentile is the number or the value of the observations just below, not equal to. And so to find a percentile, you want to find the number of people or the amount of data that is less than or equal to you, and divide it by the number of data or people that are in the studies. And again, the purpose of percentiles is to compare where you rank within people. Okay, so let's look at a couple examples. It says you and 50 other students take the ACT. You score a 29, and that is better than 43% of the students who took it with you. What percentile are you in? So that means that there are 43 students that scored less than you, but if you include yourself, there are 44 students who scored less than or equal to 29, because that, again, this should include yourself. And so 44 students scored less than or equal to 29 on the ACT. Okay, and so 44 out of 50. Nope, that is not 86, that is 88%, meaning you are in the 88th percentile. And let me get rid of that percent and write it out kind of how we would say it. 88th percentile. Okay, and again, what that means is that you scored better than or equal to 88% of the people that took it with you. Okay, careful on how this is worded. If you look at the second question, it looks like, oh, we're just going to do another example, okay? But in this case, it says your buddy scored less than 21 other people, okay? Which means he scored more than 29. I should not say he, it could be a she. This person scored more than 29 people. Okay? And so their percentile is not 21 over 50, but 29 over 50. So they are in the 58th percentile. Okay? And again, in this case, if we're talking ACT scores, the higher the better. And so comparatively, without without knowing your friend's score. So keep this in mind. If you are comparing scores and you do not want your friends to know, you could give them the percentile that you scored in, and that would at least, for comparison's sakes, let them know if they did better or worse than you. Okay? Because in this case, your friend who scored a 22 could tell you that they scored in the 58th percentile, and you knowing that you scored in the 88th percentile would know that you did better. You would just not know how much better. Okay? But that's how percentiles are calculated. Is essentially, if we think of it in terms of test scores, how many people did you do better than or equal to? Okay? But there's an easier way. Percentiles can be kind of confusing, and so we have an idea called standardized values or standardized scores. And what standardized values do is they put a percentile into a what would be considered probably an easier way to understand what the percentile actually means. It also puts the percentile in terms of the average score, which a percentile does not do, or you cannot do with just looking at the percentile. Okay, this is like the big idea in chapter 4 that we are going to be using from here on out, is the idea of this standardized score, also known as the z-score. Okay, this is the idea that is one of my favorites in the statistic community because there are so many applications of it. And so to find a standardized score, you take x, you take the observed value, okay, so like your test score, or in the example below, your height, okay, you subtract it from the mean and divide it by the standard deviation, and that is going to give you some sort of decimal, typically, not always, but typically in between 3 and -3, okay? And throughout chapter 4, we will learn what that decimal means. If you get a 1.4, what does that mean compared to a -2.7, and so on. But for right now, we're just going to learn how to calculate this. So you take the observed value, subtract it from the mean, and divide it by the standard deviation. Okay? If your z-score is greater than 0, okay, if it is a positive value, then your observation is larger than the mean. Okay? If it is a positive value, then it is larger than the mean. If it equals 0, then it is the mean. And if it's less than 0, then it is below the mean or below the average. And so what the z-score does is it tells you how many standard deviations from the mean your observation falls. That's what the z represents. That's what the decimal, or the number that you're going to get represents, is how many standard deviations from the mean your observation falls. So let's look at an example together. Okay? It says Sophia scores 660 on the SAT math test. The mean was 500. The standard deviation was 100. Jim takes the ACT math test and scores 26. The mean was 18 and the standard deviation was 6. Who did better comparatively? We have two completely different scores, two different tests, two completely different scores, and so this would not be something that we could do by just looking at your average score. Okay, a percentile would help, but in this case we don't have enough information for the percentile, but we do have enough information to find the z-score. Okay, so for our friend Sophia, she scored a 660, so that's the observed value, that's x, and the mean was 500 with a standard deviation of 100. Okay, so 60, that's 160 divided by 100, that is 1.6. So she finished 1.6 standard deviations, SD, above the mean. Okay, 1.6 standard deviations above the mean. Let's see how our friend Big Time Timmy Jim did. All right. He scored a 26 when the mean was 18 and the standard deviation was 6. Okay, 26 minus 18 is 8. 8 divided by 6. Let's see, that's what, 4/3? Yeah, and so that's like a 1.3 above the mean. And so comparatively now, oh, can't zoom out, all right. Let's just scroll down. So comparatively, Sophia did better on the math portion of the test because she finished higher, further from the mean than Jim did. And higher, remember, anything greater than 0 is higher than the mean. They both did better than average, but Sophia did even better than Jim compared to the average. So standard deviation, z-scores, mean, they all allow you to compare one individual to the entire data set or compare two individuals with each other. And so all this can be represented by a density curve. A density curve is a, we kind of drew this in chapter 3. I just didn't call it a density curve because we didn't need to know that quite yet. But notice that a density curve is the smooth curve that we had drawn in chapter 3 when we were talking about the shape of histograms and stem plots. Okay, and so we use those same descriptions to describe the shape of the graph, the center of the graph, and the spread of the graph. We can use this to describe the overall pattern. There are many data sets that follow this pattern, right? If you think about it, like here's the low end of the data set, and there's typically not very many people on the very low end. There's typically not very many people on the very high end, but most people kind of right in the middle, right? Kind of like when you take a test. Ideally, there's very few people who get Fs. If the test was challenging enough, there's not going to be as many people that get A's, but everybody's kind of in that B, C, D range is where the big chunks are. Okay, but that can be represented by what's called a density curve, and in this case, more specifically, we call this a normal curve because it is symmetrical. So your density curve or your normal curves describe an overall pattern of a data set. For this to be accurate, you can actually choose the scale. We won't actually have to do this a whole lot, but we choose the scale so that the area under the curve equals 1. Okay? And here's why. This normal curve, notice how it doesn't exactly follow the data, right? The red line, the blue bars go above the red line here, but then this blue bar is below the red line there, okay? And so by creating a data curve where the area underneath is exactly 1, we then normalize this data. That's why it's called a normal curve. We normalize the data, and although it might not be super exact, it is a very good estimate. Okay? And so that's why we have our density curves equal have an area of 1 underneath the curve. Okay? So the density curve idealizes the shape of the distribution. Again, idealizes it, meaning that it summarizes it. It doesn't follow it exactly, but it gives you a good idea of what it looks like. And as we'll see throughout chapter 4, it is the most useful when we are describing a very large data set. Okay? All right, I'm just going to stop there for now. So in general, we call these density curves. Both this and then this bottom picture here are both called density curves. But in particular, this curve is called a normal curve because, as we discussed on the previous slide, it normalizes the distribution of data. Okay, what we'll be able to do throughout chapter 4 is, based on where a piece of data falls on the normal curve, we can predict what percentile it's in, how many standard deviations above or below the mean it is, which again we call the z-score. And so again, we're talking density curves in general, but specifically normal curves. And so normal curves have all of these characteristics because again, we have normalized the data. And so on a normal curve, the median of the curve has half the data on the left and half the data on the right. And you'll notice labeled in your picture here that the mean and the median are actually the same on the normal curve. Okay, and they are right in the middle. All right, and so in a normal curve, half the data is to the left of the median and the mean, and then half the data is to the right. Okay. What we'll learn is that just like box and whisker plots, the normal curve, and again, density curves in general, but the normal curve can be divided into different quadrants. Okay. And so your first quartile is when there is 1/4 of the area under the curve is to the left. So everything under here represents 1/4 of the area of the entire curve. Okay? Whereas everything, let's do it like this actually instead. For Q3, everything to the left represents 3/4 of the area, or 3/4 of the data. Okay? And so again, every chunk is divided into fourths, even for normal curves. And so we can estimate the area and under of each curve by dividing the data into 4 equal parts. And again, the mean is right in the middle. That's what normalizing a distribution does. It puts the mean right in the middle. We won't spend a ton of time talking about skewed distributions. Again, we saw this a little bit we talked about this a little bit with histograms and things like that, stem and leaf plots as well. When a distribution is skewed, one common question is how does that affect mean and median? Think of the mean as the balancing point, okay? And so the mean will typically be more towards the center of the distribution, whereas the median pulls away from the long tail of the smooth curve, okay? So notice in this just general example, your mean, again, kind of towards the middle of the curve, where the median is further away from that long tail. Okay, because what this distribution kind of implies is that a lot of the data is right here, and then the data just kind of tails off as you go. And so if a big chunk of the data is here, the middle is closer to the big chunk of data. Remember, the definition of median is that it has half the data, or it divides the data in half. Okay, that doesn't change. And so if I were to just give you a sketch of a different graph going the other way, so here's your tail, and it looks something like that. Again, your median would always be closer to the tail than your mean. Okay, if I kind of color coordinate there, green is mean, red is median. All right, so your median will always pull away from the long tail, because if a lot of the data is clustered here, then half of the data is closer to the cluster than if it's than the super spread out part. Okay. And then another type of density. So we have different types of density curves. We have the normal curve, which is basically what chapter 4 is about, so we'll talk a lot more about that. We have the skewed distribution, where the data is tailing off. We talk skewed right or skewed left. And then we have a third type of distribution called a uniform distribution. Now, uniform means that everything is equal. Okay? So with density curves, with distributions, the area under the curve is always supposed to be 1, okay? Because we, again, have normalized the data, and so for it to follow that pattern, the area underneath always has to be 1, okay? So a uniform distribution, again, means every bin is equal. And in this case, it says intervals 0 to 5. So think about it like this, all right? Draw a line, starting at 0, 1, 2, 3, 4, and 5, okay? But if it's uniform, again, every bin is equal. And so if the 0 to 1 part of the chart is that big, then 0 to 2 is that, or I'm sorry, 1 to 2 is that big, 2 to 3 is that big, 3 to 4 is that big, and 4 to 5 is that big. Again, uniform means that there is an equal number of data points in every bin. So it's not actually a curve. A uniform distribution is more like a rectangle. Okay? And so the question is, if the interval is 0 to 5, so think about it this way. If this, let's call it units, if this is 5 units long, the question is, what is the height of the distribution? Okay? Now, remember, for density curves, the area underneath has to be 1. The area underneath. And so if this is the top of my density curve, everything below that needs to have an area of 1. Notice we have a rectangle here, and so this is just basic geometry. We know that the base, or that the area formula for a rectangle is base times height. We know the area has to be 1. We know the length of the base is 5 units. So the height of our distribution is 1/5, okay, or 0.2 units. And again, the reason, the y of it, is because the area underneath the curve is supposed to be always equal to 1. So 5 times 1/5 equals 1. Okay? In a uniform distribution, again, every box is equal. And so even though we don't know anything about the data from this box, we will be able to predict what percent of observations lie from 1 to 1.5. Okay, think about it like this. Every box represents 20%, right? Again, it's uniform. So 20% of the data is in each box. There's 5 boxes, 20%, 5 times adds up to 100%. And so the question is, how much of the data lies from 1 to 1.5? So from 1 and then 1.5 would be about half the box. Okay, so if the entire box is 20%, half of the box would be about 10% of the data. Okay, and again, this works. We're able to do this because the data is uniform. Every box contains the same amount of data. What are the median and quartiles of the data? Well, remember, median splits the data in half. Q1 is the first quarter, Q3 is the third quarter, okay? And so even though we don't know anything about the data, we can find Q1 by taking 5 times 1/4, which is, let's see, 5/4, so 1.25 is the first quartile of this data. Okay? Again, even though we didn't know any of it, because it's all uniform, we're able to calculate this. For the median, it'd be 5 times 1/2. So 2.5 is the median of this data because it's all uniform. And then the third quartile is 5 times 3/4, which would be 3.75, would be the third quartile for this data. And again, we are able to just assume all of this because of the word uniform. If the data is 5 units, if it has 5 bins to it, and each bin is equal, then the first quartile will happen exactly at 1/4 of the data, and then 1/2, and then 3/4. Okay? So if we were to just apply this to get back to normal curves here, notice that this data is shaped, like a normal curve. Again, I just sketched it, but your normal curve will never perfectly fit the data. Okay? But again, even though we don't know each individual data point, because we have this understanding of what a normal curve is, we are able to estimate that the mean and median of this data point. First of all, it's a normal distribution. So because it's mostly normal, meaning that, again, it's symmetric, the mean equals the median. And it looks like, again, we're just estimating right now, but it looks like 12 hours would be the estimated mean or median here, because that's, again, right at the middle. It's right at the peak there of your distribution. Again, I just kind of drew it by hand, so it's not absolutely perfect. But again, notice these gaps. This is when we talk about area under the curve, this is what we talk about, is these little gaps that we have. By normalizing that area, we can then make predictions based on this data set. Okay, so if you sleep, or what is this, counts of first lightning flashes. Sorry, I said sleep. But so if you have 15 hours after midnight, we can estimate what percentile you're in. Okay, and give you and tell you what standard deviation that is. Okay. So that's 4.1 to 4.3, just a very general introduction into density curves. Okay, remember that's kind of the overarching topic here is density curves, and then there's three types. There's normal, there's skewed, and then there's uniform. Okay, and moving forward, chapter 4 is all about normal density curves where they are symmetric. Okay.